In this segment, we'll discuss the effect of shifting bits left and right within a binary number. As we'll see in an upcoming code example, many ARM instructions permit bit shifting, moving the bits in a register or in a constant binary value some number of positions to the right or to the left. For instance, here's a 16-bit example shifted to the right and also to the left by 5 bits. So you can see that we've shifted these bits over to be here instead, and then in the case of a right shift, the last 5 bits are simply lost as they're shifted off of the end, and these bits here are shifted to the left from here, and again extra bits are simply lost as they're shifted off the left end. Now, bit shifting can be used to create and analyze bit patterns within a register. We'll see examples of this in an upcoming example, but bit shifting also has a mathematical effect, which we'll look at here. Consider these unsigned 8-bit examples of shifting by left 1 bit. 0000110 shifted left to this value, and then this value here shifted left by 1 to this value. What exactly are their numerical values before and after left shifting? And what does this suggest about the mathematical effect of left shifting? Well, if you think about it, this here is a 6, and it shifts left to this value, which is 12. And this one here, a little larger, is a 42, which shifts left to a value of 84. So it looks like left shifting has the effect of multiplying by 2. It makes sense that left shifting would multiply a number by 2, and you see that each bit is moved up 1 position and thus has 2 times the numerical value it had before shifting. The same sort of multiplication occurs when shifting a base 10 number left by 1 digit. For instance, 123 left shifted to 1230. Each digit has 10 times its pre-shifted value, and the number is therefore multiplied by 10. And left shifting by more than 1 position, of course, repeatedly doubles the value, redoubling as many times as we left shift. So here's question 2. Given that the 8-bit pattern for 5 is that, what is the pattern for 80? Note that's 5 times 16. Do that by left shifting. If you think about it, multiplication by 16 is 4 doublings. So we need to shift left by 4 positions. So if this is 5, then that is 80. If left shifting doubles a value, then shifting to the right divides it by 2, since each bit moves to a position that is half as valuable. For instance, if we have the value 70, then that shifts right to become 35. But right shifting is more complex in 2 ways. First, consider what happens when we shift an odd value. Let's try 7, for instance. The result is 3, and the rightmost 1 is lost. The effect is that the division of 7 by 2 is truncated from 3.5 to 3. In other words, right shifting divides by 2, discarding any fraction. By the way, since we're talking about shifting bits off the bottom end of a number, it is worth noting that binary arithmetic can be extended into fractional places, just like decimal. The decimal system has a tenths place, a hundredths place, and so forth to represent fractions with arbitrary accuracy to the right of the decimal point. We can do the same thing in binary, adding a binary point with positions after it, representing 1/2 and 1/4 and so forth. If we do that, then shifting 7 by 1 position to the right gives 1/1 0.1, and that is binary for 3.5 since the 0.1 is in the 1/2's place and represents 1/2. If we shift it to right again, we get 1.11, and that's 1.75 in decimal because the 0.11 is 1/2 and 1/4. So a question, just to be sure you got the idea there, using fractional binary places, how would you write 1.625, which is also 1 5/8? How would you write that in binary? The answer is that you'd write 1.101, which is 1, of course, plus 1/2, plus 1/8. We'll look more at binary fractions when we discuss floating point numbers later in the course. For now, all fractional bits are simply dropped when we right shift. The second complexity with right shifting comes when right shifting signed negative numbers. So consider the case of right shifting this to get that. Now, the division by 2 rule works fine if they're unsigned, because this first value here is 252, and it right shifts to become 126. But, question 4, what about the signed case? What are the signed values of those 2-bit patterns? Is the signed value of this equal to 1/2 of the signed value of that? Well, the answer is that in signed form, 6 1s and 2 0s is a -4. But 0 and 6 1s and 0 is still 126. Half of -4 is -2. And that is the pattern 1 1 1, 7 1s and a 0, which would then be correct. So in order to preserve the mathematical effect of division by 2 when right shifting a signed value, we have to use sign extension, which means we fill in on the left with whatever the MSB is. And in particular, when we right shift a negative signed value, we fill in on the left with 1s. If we're shifting to the right to divide by powers of 2, then sign extension is appropriate. If we're more interested in the bit patterns than in the mathematical value, then extra 1 bits on the left are a nuisance. Almost all assembly languages, including ARM, let you choose between a logical right shift, which does no sign extension, and an arithmetic right shift, which does. And then one final point. All the shifts we've done so far simply dropped bits off of the right or left end. But there is another possibility. In a right shift, for instance, we could move bits shifted off the right back around to the left end of the number in circular fashion, almost as if the bits were on some kind of a chain. So right shifting, say, 0 1 1 0 0 1 0 1, circular right shift by 3, and we would take the 101 bits here and put them back around on the left side, so we'd get 101 011 00. And the bottom 3 bits are not lost, they're simply rotated. Most CPUs, including ARM, offer this shifting option, but it's less common than the others because it lacks a clear arithmetic meaning.